Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics. We're in Chapter 3, part of this playlist, which I'm calling Continuous Random Variables. And let's jump to today's topic, which is expectation of continuous random variables. In this section, we'll assume that we have a continuous random variable, x, with known density f. Let h of x be a function of a random variable, x, which is itself a random variable. The goal of this section is to find the mean value of h of x. Note that these expressions are all equal. Mean value, average value, expected value. So the definition of expected value is this. Let x be a continuous random variable with density f. Let h of x be a random variable. The expected value of h of x, denoted by e of h of x, is given by this, the expected value of h of x. What this says, take h of x times its density value integrated over all possible values of x. Now, special cases of h of x are of interest to us. So the expected value of x. So h of x is just x, and it's denoted by the Greek letter mu. So the expected value of x is you take x times its density integrated over all possible values of x. And that's it. That's the mean value of x. The expected value of h minus mu squared, another specific value of h of x. Now this is denoted by sigma squared, called the variance. Sometimes we'll just write it var of x. And this is how you define it. The sigma squared equal to the variance of x equal to the uh, average squared distance from the mean is equal to, you take that value times its density integrated over all possible values. Another one is the expected value of e to the tx. So h of x we set equal to e to the t of x. So this is denoted by mx of t, called the moment generating function, and as previous specific cases, the expected value of e to the tx, take that times its density integrated over all possible values. Now the rules for expectation: let x and y be continuous random variables, and let c be any real number. Then the expected value of c is equal to c, right? So what's the average value of a constant? Well, it doesn't change, so the average value is itself. The expected value of c times x is equal to c times the expected value of x. Expected value of x plus y is the sum of that expected value of x plus expected value of y. Now we'll prove number 3 and leave the remaining as homework. The expected value of x plus y. Now notice there's two variables here. So we take that quantity times its density, f of xy, integrated over all possible values of x and y. Let's multiply the density into each value so we get x, and then this is the y. Now, for this second one, since we're integrating x first, we can take the y out of the first integration. Here we switch the order of integration, and all the densities that we're going to use in this playlist, you can switch the limits of integration, even when there's an infinite there. So we integrate y first, which means we can take out x. But when we integrate over all possible values of one of the variables in a joint density, then that leaves the marginal density. So we integrate out y, that just leaves f of x. And over here, we're integrating out x, that leaves f of y. Well, these are the definitions of expected value of x, expected value of y. And that's what we wanted to show. Now, computational formula for sigma squared, and we will use this formula almost in every video when we derive the variance of a random variable from a specific continuous distribution. So the variance of x is the expected value of x squared minus the mean squared. Now some, instead of saying mu, will put in expected value of x. These are the same. Now, just by definition, the variance of x is equal to the average squared distance from the mean. But we can square this, and we get x squared minus 2 mu x plus mu squared. Expectation is what's called a linear operator. It goes into each term, so we get the expected value of x squared. The 2 and mu are constants, so it just goes into the expected value of x plus this constant mu squared. Well, the expected value of x is mu, so we get minus 2 mu squared plus mu squared, which is minus mu squared. We have x squared, which is this quantity here, and that's what we wanted to show. Now, the standard deviation, let x be a random variable with variance sigma squared. The standard deviation of x is just given by sigma, which is the square root of the variance of x. Now, the nice thing about standard deviation, it puts the units of this measure of variability back in the same units as the random variable itself. Now, the variance is in squared units, which is often not as useful as using the standard deviation. Now, rules for variance: let x and y be independent random variables and let c be any real number. The variance of a constant is equal to 0. There's no variability. It's all constant. The variance of c times x is c squared times the variance of x. So the c comes out squared. The variance of x plus c is equal to variance of x. And to me, what this says and what I visualize is you have your data and think of it all sitting on a number line. If you just move it to the right, c units, the variance of your data hasn't changed. You just moved it to the right. And so the variance is still the same, variance of x. Now, the variance of x plus y is equal to the variance of x plus y. Remember, x and y are independent. Now, we'll prove number 2 and then leave the remaining as homework. The variance of cx is equal to the expected value of cx minus cu, quantity squared. That's the definition of the variance. We can left factor out of c and then take it out of that squared. But this is a constant, so it can come out front. And well, this is the definition of the variance of x. And this is what we wanted to show. Now, here's a quick R illustration. Now, some of the distributions that I'm going to list in here, we're going to cover in later videos. So for now, you just need to know that they're continuous distributions, or the random variables that create these are continuous. So first we'll look at a normal distribution with mean mu and variance 25. Now, if we integrate x times that density of the normal with mean mu and standard deviation squared of the variance, and we integrate it over all possible values, we get 2 back. And as we should, that's the mean. Now, if we integrate x minus mu quantity squared of the density of a normal density with mean 2 and variance 25 over all possible values, we get 25. So that's the variance, as we should. Now let's go to a beta distribution. There, it's a 2-parameter distribution. It needs alpha and beta. We're going to let alpha be 2 and beta be 3. We're going to integrate x times that density, the beta density, over all possible values, and we get 0.4. I'll show you that that's correct in a second. But I wanted to also show you that even though the beta distribution is only defined from 0 to 1, you can still integrate it over all possible values, because when you're outside of 0, 1, it takes on the density is 0. Okay, so to illustrate that, let's integrate x times that beta dense distribution just over 0, 1, and we get 0.4 again. And later in a video, we're going to show you that the mean of this beta distribution is alpha divided by alpha plus beta, which is 0.4, which is the mean that we just achieved up there. If we integrate x minus mu quantity squared of this beta distribution or density from 0 to 1, we get 0.04. And in a later video, we'll derive this formula for the variance. So we plug in those values and we get 0.04, which is the same. Okay, we're right at 10 minutes, so I will stop. And I'm going to peek at what the next video. It's the continuous uniform distribution on an interval. Well, I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.